Recording is on.
Oh.
Hey guys.
Hello.
I'd already set the recording to start. I don't know why it stopped, but anyway. No. I mean, it stays on, but anyway. But did somebody else invoke a recording? No?
Okay, let's get started here. We got 10 people, not bad. Okay, good evening, everybody. Welcome to our mid-November meeting. Don't see anybody new, and we're ready to go. So today or tonight, we've got two presentations. One by Peter, LT Spice Mini Rabbit Hole. And then Dave is going to talk about his self-balancing robot. Which one of you two want to go first? Flip a coin. Go ahead, Peter. Go ahead.
Yeah, might as well, because Dave's the feature presentation, right? And doesn't the cartoon go first? Anyway, no, after Dave's presentation of his final in the series of rabbit holes, where Dave was showing us all kinds of fancy measurements to do in LT Spice, I thought, okay, that seems pretty good. But so I took a spice simulation I had from way back when I was doing LT Spice in the real world, the common emitter amplifier, and I thought let's try some of the stuff that Dave was showing us on a more simple, on a basic simple simulation and with some simple statements, and it seemed to go pretty good. I think I understand most of it. Well, there's a couple spots I'm not 100% sure. Maybe Dave doesn't can answer what it is, and I'll just show you what I did. It's nothing big and fancy, but it's a start. And you got to start somewhere, right? Okay, you can see that?
Yes, sir.
Okay, so when Dave was showing the measure statements, I thought, okay, well, let's break it down to something really simple so I can understand it and write it out. And, and that's what I did. When you talk about LT Spice and how you make measurements with the waveforms, we know there's, well, basically, from my understanding, there's three ways of doing it. And basically two different ways with the cursors, and then there's this way that Dave showed us using the Spice air log. So what I did was I started off with the easy one first. Is like, okay, define like this variable here, output, and I'm going to go measure for the peak-to-peak voltage, and it's the output, and it's important that this one here is spelt exactly how you have it spelt down there. And again, the other one's the input, same thing, peak to peak is what I'm doing. And then I thought I'd try something a little bit different and not make a measurement, but try to do a little bit of math. So an easy one is gain. And of course, it's just, it becomes a parameter. And you've already had Spice calculate out the input and the output. So try output divided by input. Then I got carried away to try RMS because I was on a roll. So that was all fine and good. And then I thought, you know what, it might be interesting to do is to measure frequencies, because, when you put your cursors on the waveforms, you may not get them exactly where they need to be. So, well, that would be true for voltage as well. So I thought, okay, well, let's see what we can do with frequencies. And I didn't come up with this on my own. I had to do a little bit of Googling and searching around to see what it means. So your variable here is the T1. So in your Spice air log, you'll find T1 will have this value in it. Find the time when the voltage on the output equals 0 rise 1. Now I understand what's going on here as far as you need 2 points to find the 2 points in order to calculate out the frequency. But maybe Dave has the answer to this. What's rise 1, rise 2? What's it actually doing there? Is it kind of, is Spice going up to rising to a peak or the beginning of it? Do you know, Dave?
No, I don't know. I'd have to look up the documentation. I think rise 1, rise 2 might be a definition you set up for, a rising edge.
Right. Yeah. So like I say, I'm not sure exactly what it's doing. All I know is it works. And anyway, so then we got that in there, and then of course in the calculation for frequency, and you put it as in the parameters, the 1 divided by the T2 minus T1, and everything else is this circuit. We all know what that's all about. And again, up to the view, and then to the spice air log, and then as we've seen before, that all your variables are all spelled out here on the left with your with the results here. Now,
Hey, actually, Peter, you know what that rise 1 and rise 2, as you're talking about frequency, what that is? I
what?
suspect it's the first rising edge and the second rising edge of a signal. That's why you get in the frequency.
So like
You
it's
get in
doing,
the first rising edge, and then you get in the second rising edge, and that is the period of the signal.
It's
And 1 over the period's frequency.
it's rising through 0, isn't it? It's rising through 0 volts. That's what it means.
okay. I wondered.
V out equals 0. A rise 1 is V output 0. That's 0 volts on V output, and it's
Yeah.
they're calling rise 1, rise 2 because you got 2 things to deal with. So it's the first and second one, I think. First one and second one.
Yeah.
First time it goes through 0. Second time it goes through 0.
I know. I did take a look early on, but I couldn't get that. You could not get down to the time 0.0004, 4, etc. Because I wondered where would that measurement? Sorry, not there. This one here. Where was that time frame? Oh, that's the same thing. Anyway, but to that point, I noticed here, like for example, like I'm telling Spice to do a 1 kilohertz sine wave, and it's 999 point, so it's not quite there, close enough. And same thing with some of the voltages. They're just off ever so slightly. So I'm thinking, and I haven't done it yet, and I'm not 100% sure how to do it. I have to do some reading and searching, but delay the start when it starts to make its measurements. And I'm thinking that might maybe, that way the waveform settles down a bit, and then that might make it a little bit more accurate. And then I guess if you put it down a little bit further into the waveform where it starts to do the reading, that would put push this time out a little bit further, and then you might be able to take a look at the waveform viewer and actually see where this time crosses. And maybe like you're to your point, Michael, it's at when it rises above the 0 line. Anyway, that's what I got up to. So I thank Dave for this little mini rabbit hole that I went down.
I'll duplicate this myself out of curiosity just to see.
It's a good way to learn how to use some of those commands. You're shown how to do something, but really it takes to go do it yourself. And when you look at some of these more complex simulations, this really becomes important because you just couldn't sit there with your waveforms, the multitude of waveforms, and with your cursors trying to measure off. You'd be there for days. Anyway.
Dave had his hand up.
Dave.
Yeah, Peter, I think you're getting hung up on numbers here, okay? Because there's no way you could measure something to 7 decimal places.
I realize that, Dave. It's a curiosity as to where is rise 1, rise 2 going across the 0 line. I'm not going to do that for sure.
Let me finish. So that's the first thing, okay? To measure frequencies to 2 decimal points, again, very difficult because you're talking about, microhertz, or not micro, it's millihertz. But the other thing too is an LT spice, it defaults to a low floating point precision. So what you're seeing there is round off error. If you go in, there's a num digit parameter,
right?
That if you set, it'll increase the resolution of your numbers, and you may see it round up higher. But if you were to round this to 2 or 3 decimal points or to an integer number, it'll come out exactly what you expect it to come out to be.
I see what you're saying. Okay, I understand now. Okay, good. Thank you.
So yeah, don't get hung up on the precision of these numbers, because this is a simulator, and it's only good within, I don't know the percentage, but it's probably only good within 10% or something, right?
Yeah. Okay, good. Okay,
Anybody else? No, I guess he's right. Okay, thanks, Pete.
Thanks.
Take it away, Dave.
Can you guys see my screen?
Yeah.
Yep.
Oh, shit. Hang on, I'm just turning on recording here. There we go. Okay. So my presentation today is on the balancing robot that I built. And I've been building this over the summer on a whim. But, I'm really inspired by what Peter did there. And I'm glad Peter's going outside of his comfort zone. And, he's willing to make mistakes and challenge his boundaries there. And this is a quote from Dean Kamen. I don't know if you guys know who Dean Kamen is. He is the inventor of the Segway, the original balancing robot. He's also, he made his money from doing water purification on kidney dialysis machines. Because the water, when you do kidney dialysis, the water has to be extremely pure to clean your blood, right? And also, too, he's the founder of First Robotics, and that's how I know of him, is through First Robotics. So here's another quote from Elon Musk, and I'm glad, Peter's, is challenging himself and going beyond his comfort zone. That's great. I really enjoy seeing that, and I hope that's I had a small part to play in that. But so I'm hoping that these talks I give is going to help encourage everyone to go and push their comfort zone a little bit and take on something complex. And that's what Elon Musk said. I don't know if you know how many times Elon Musk failed in getting those rockets to go up and land by themselves. It's like the amount of failures that guy had, or his company had, was just unbelievable. But eventually he got it to work right. So this is about a self-balancing robot, and more about something called IMU, an inertial measurement unit. And what that is something that allows you to measure your orientation in space. So like rockets use that, and aircraft use it. The autopilots still have some kind of an IMU on board. So okay, I don't know what happened there, but my screen just froze. But okay, so back in 2009, okay, come on, go away. Yeah, back in 2009, I built this autopilot for an RC airplane, and basically what it had gyroscope, an accelerometer as a pressure. That's a pressure sensor to measure altitude, and behind here was a PIC 18F chip, and these pins were to control the servos to make the airplane turn and pitch and roll and stuff. And so I wrote this code. I got it working. I never saw it through. It was measuring, pitch and roll and yaw accurately, but I couldn't get it to control servos properly. So I abandoned it. I stopped working on it, and I left that. That's been sitting now for years, since 2009. So since then, the whole IMU market has matured. This came out shortly after I was working on it. It's one of the first IMU boards that got developed, and it came out from SparkFun. SparkFun developed this board. They had software for it, and they were selling it, and that was circa 2010, 2011-ish. You know, that board came out. Today, there's a ton of these IMUs around, and I got back interested in it. Is that the drone I built a drone from scratch, a high performance racing drone from scratch, and that needed these the flight controller here, which is basically IMU and a controller to control the various motors. And I bought this little drone here. This is like $100 drone, and this board comes with a IMU in it to control and balance the drone. So back in, I think I got my license, my amateur license in 2010, 2011. So amateur radio, you know, kind of distracted me until this year when I got back into building drones and airplanes and looking at IMUs. So basically, my radio's down at the bottom of this bomb here. This some days, that's what I want to do with my radio. Can you guys hear me okay?
Yeah, it's all right.
Okay. So for my balancing robot, this is the build I used. I 3D printed a frame. It's got 2 stepper motors. I 3D printed the wheels. Okay, and I, instead of going and etching a board, I just did a development board where I would put a nano and put my power. Here's my power rails, +5, 12, and ground, and I would just run wires. You can see here all the wires. These are for the 2 stepper controllers, and that's for the IMU. I bought the off-the-shelf IMU. They're so cheap now, you can get them for a few dollars. There's the IMU there, and that's got an accelerometer. It's got a gyro, 3-axis gyro, and I don't know if it's got a pressure sensor. I don't think it has a pressure sensor for measuring altitude. So how does this work? How does a self-balancing robot work? So if you take a look at a helicopter, this is the best example. So you've got the helicopter blade turning in one direction. Okay. Now Newton's third law, every action has an equal and opposite reaction. So because the blade is turning this way, the body of the helicopter wants to turn the other way. So if you turn the blade this way, the body wants to go this way. That's why you need to have a tail rotor. And the tail rotor balances out that torque. And if you look at some trucks that are moving off, you'll see if they've got a really heavy load and they're moving off, the whole truck will twist. And that's just because of the torque, because they're putting so much torque to get these wheels going that it's easier for the truck to spin than it is to spin those wheels. And the gearing, they've got such high gearing or low gearing, you know, that it's easier for the truck to spin than it is for it to spin the wheels. So basically in a self-balancing robot, it's the same thing. You know, if you want the robot to go to spin in this direction, you spin the wheel in this direction. So, you know, again, Newton's third law, this reaction does an equal and opposite reaction in the other direction. So if you spin the wheel this way, the robot's going to try and tilt this way. Same thing. If you spin the wheel the other way, it'll try and make the robot go the other way. So by you spinning this wheel, you can make the balance, the robot balance. So the trick is to equate the angle at which the robot tilts, either forward or back pitch. We'll call this the pitch axis. So if the robot pitches back or it pitches forward, the angle at which it pitches to figure out how fast to turn the wheel. That's the rocket science behind this. So basically, so here's my requirements I had going into doing this. Well, first requirement was I need to spin the wheels. I need to set direction, and I need to set the speed. So with those stepper motors, I had to figure that out. How do I set the direction? How do I set the speed of that those motors? Next, I need to measure the tilt of the robot, the pitch. Is it pitching forward? Is it pitching backward? Things in yellow are things that I had to figure out subsequently, things which I didn't realize I had to do, but it's something I had to do towards the end. And the other thing I had to do was to figure out the turn. So not only did I have to look at the robot pitching this way, but the robot turning, going, the robot turning around. So I had to look at the how much the robot turned around the vertical axis. So I needed to also set the direction speed of the wheels based on the pitch. I wanted to use an Arduino Nano and a LiPo, and I didn't want to use any libraries. I wanted this to be completely homegrown because that's how I learn, is I try and do things myself. So the other thing, I wanted to use Platform IO and Visual Studio. I don't use the Arduino IDE anymore. I've stopped using that. I only use Platform IO now, and it's very, very powerful. So based on these requirements, I started building, and then these are some other things which cropped up, which I didn't foresee. One is that LiPos have a minimum voltage. And if you drain the LiPo beyond a specific voltage, you damage it. So I had to jerry-rig a circuit to monitor the LiPo voltage to make sure I don't overdrain it. Troubleshooting was a huge problem with this, because this is very timing critical. And you can't, use a serial.print to print out numbers, because it wouldn't work. So I had to flash LEDs and use the scope to trigger pins and do things. And that's how I would troubleshoot that. And so that was a huge hurdle there. The other thing was protecting the robot from falling. You'll see here that I have these sticks. Well, guess what that was for? That's to protect the robot from falling, because the robot would fall over and would smash its face, right? And all my electronics is there. And so I had to quickly, figure out how to keep the robot from falling over. The other thing was rubber on wheels. So you could see here, there's elastic band on the wheels, but the original build, there's no elastic band. Okay, and those wheels on this floor, they would just spin. There was no traction whatsoever. So I had to go back and put elastic bands and glue elastic bands on the wheels, and that became the tires. And then tuning the PID, I had a huge headache doing that. Finally, I had to, my no libraries, 100% homegrown. I had to go use someone else's code to get the PID, and you'll see why in a second. So I'm going to cover off a couple of things very, very quickly. I'm not going to go into details. So the first thing, high-level view of a stepper motor. So I've got two stepper motors, and I control the stepper motors based on direction, and you could set the speed of them. And basically they work. They have a permanent magnet in the middle, and they're brushless. So that's why they've got a permanent magnet in the middle, and they've got coils on the outside, so there's no brushes, right? So by you energizing two or more of these coils, you could make the rotor here turn a small amount, a step. You could make it step. So you make it step a little bit, turn a little bit, right? And by you changing which coils, you can make the step bigger or smaller, and enter in a driver. So this is the A4988 driver. It's one of the most popular drivers, stepper motor drivers on the market, especially in the Arduino maker space. And so most of these stepper motors, they're 4 wires, and that's what controls those coils. And so this puts out a lot of current to the stepper motor, and you've got various pins here that control how much it turns, how fast it turns, and which direction. So for example, the way that it turns is set by this direction pin. If it's high, the rotor will spin in one direction, and if it's low, the rotor will spin in a different direction. So your microcontroller would control that pin to set the direction that it would turn. And then there's the step pin. So what that is, the falling edge of a pulse would cause it to advance one step. So here you could see the falling edge, rising edge, then a falling edge. So it's only the falling edges that are making it step. And guess what the time between that falling edge is? That's the period of a signal. So this is just basically a frequency. You're sending out a square wave frequency, and that period between the rising edges sets the speed of the motor. So, and they also have these pins here, MS123, and that sets something called microsteps. So in this case, by setting those pins, 1 or 0, setting a +5 or 0 on those pins, you can cause it to do microstepping. By default, I use the Nemo 14 stepper motor, which is the same that's used in 3D printers. And so I use the same stepper motor, and by default, one step, so one pulse, causes this shaft to turn 1.8 degrees. So you could set this up so that, it'll take 16 steps to go 1.8 degrees. So that means you got to generate 8,200 pulses for this shaft to go around once. And you can set it for 8 steps, 1,600 pulses, blah, 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 blah. So those pins allow you to set the resolution of your steps. So as I said, it's the frequency of the falling edges that's going to set the speed. So if you plot the period versus the speed at which it spins, you'll see it's a 1/, relationship. And this is what causes grief for the PID. It's not a linear. PIDs assume a linear behavior. So you change a number once, you change something once, and then it's the output's going to be 4 times or 3.2 times. It's a linear relationship between the input and output. But in this case, it's a non-linear relationship. And I tried writing code for this myself, and it caused me all kinds of grief. So enough about stepper motors. So let's talk about measuring pitch. So you could use an accelerometer. An accelerometer measures force applied in the X, Y, and Z planes. And it also measures the acceleration due to gravity. And that's what you use to measure pitch and roll with accelerometers. You could also use a gyroscope, but a gyro measures a turn rate. It measures a rate. So you have to take the output from the gyroscope and multiply it by a time to get the angle. And so you can get data from either one of these. And the problem is gyroscopes drift in time. There's no concept of flat or level. And accelerometer gives false readings for real acceleration. So if your board undergoes a real acceleration or a vibration, it'll give you a false reading. So the trick is to combine the outputs of both of these sensors together to get a more accurate reading. And so that's the most famous way of doing that is using the Kalman filter, which is what I used way back when, but it's a lot more complex. The complementary filter is what I use, and it's a lot simpler to fuse the data together. So just a little bit about the MPU 6050, which is the MPU, the IMU board I use, which has an accelerometer and gyro. So it measures roll. So the gyro measures rate of rotation around each axis. here, right? Now, and the accelerometer measures acceleration around each axis. So when this is flat, it's going to see a 1g acceleration due to gravity. So the minus g axis will come out and say it's 9.8 meters per second squared, right? Or an acceleration of 1, right? We say that's 1g, right? So it'll measure minus 1g. So the way this works is that if you look at a rotation around the x-axis, so I'm going to rotate this thing around the x-axis here. So I'm going to flip, this end comes up, that end comes down. So I'm rotating around the x-axis. So the plus z-axis moves and it's over here, and the minus y-axis comes up here. This is called my pitch. So, and that's what the accelerometer will give you. It'll give you that angle. Same thing with the, if I measure a rotation around the y-axis, my x-axis comes up, my z-axis, sorry, will come over here, and my x-axis comes up here. And as well, the gyro, in this case, the gyro will give the roll rate around the x-axis, and in this case, the gyro will give the roll rate around the y-axis. Enough said about how these things work. So the mounting that I have on my robot is I have it mounted upside down. So here is the IMU. This is the MPU 6050 here. The plus Z axis is coming up this way, but here I'm looking up at the robot. So the robot's upside down here. This is upside down. This is the robot looking down. You can see this is mounted upside down. So the minus Z axis is coming up, minus the plus Y axis is here, and the plus X axis is coming out of the page. So that caused me a little bit of grief to figure that out. But to get the angle, it's just you're using trigonometric, like high school math. Like you're just using trig to get the angle. You're looking at that rotation, you know, about for example, the y-axis. You could use trig and you could figure out what that angle is, and that's what I'm doing here. I won't get into that. Same thing with the gyro. The gyro spits out a value around the y. If I multiply that by the time between my measurements, it'll give me the actual angle. So for example, if I make a measurement every 4 milliseconds, I just have to multiply the number that's spit out by the gyro by 4 milliseconds, and it gives me the angle. So that's it. That's all I want to talk about, that stuff. So here's the code. I'm not going to go through the code, but basically I am sampling that board every 4 milliseconds. There is a interrupt that goes off, and it sets a flag, and I go through and I read the MPU 6050. I figure out the time between my values, and I compute the values, and then I compute my PID, and I spit out the PID to the wheels to make the wheels spin. And this is how I calculate the various pitch and accelerometer angles and gyro angles. So here's the first test that I did. I've got it wired up. I finally got the MPU working. And so this is the first test I did of just making sure that it's actually working properly. So right there, it's spitting out the angle, the pitch angle, and it's coming out 0 for all intents and purposes. So now I'll put it at a 45-degree angle. And see, it's spitting out 46, 47 degrees, close enough to 45 degrees. That's not bad. That's pretty good. So next, I had to figure out how to get the stepper to work. So that was a real pain in the butt. So I had to interrupt, go off every 20 microseconds. And that I would have a counter to count how many pulses I would have, or what the delay between the pulses is. So that would be the period between pulses. So I had every 20 seconds, I would count like 5. So 100 microseconds, and I'd pulse the step control, and I'd set the direction. And so this here is a little test program I wrote to get the stepper motor working. So there you can see the wheels spinning. And then I do a more aggressive test where I do random steps. And you can see the wheels, they're randomly going in different directions here. Are you guys seeing this? That's okay?
Yeah.
Yep.
Yeah, absolutely.
Okay. So the next step was the PID. So I was able to measure angle. I was able to spin the wheels. Now how do I marry it together? So a PID is a proportional integral derivative controller. It's a feedback controller. So basically what it is, you take some kind of sensor input. So you take some value, you take a set point of where you want that value to be, and you calculate 3 terms: a proportional term, an integral term, and a derivative term. You sum it and you feed your controller that. So in the case, suppose my angle, I'm getting my pitch angles coming in and it's saying it's plus 10 degrees, but I want a pitch angle of 0. So I've got, they call it the error. I've got an error of 10 degrees. So I've got a pitch angle of 10. I want 0 coming in, my set point 0. And so I've got an error of 10. I feed that into a proportional term, an integral calculation, and a derivative calculation. So the proportional term is very straightforward. It's just the error, the difference between the set point, multiplied by a constant. And so this is proportional. So this makes the robot get a real jerky, or if you use a proportional term alone in your PID, you get very jerky movements, because it's as good as this constant here, and of magnitude of the error. The integral term is you're taking the sum of all your errors and you're multiplying it by another constant. So what this does, think about the integral term, is if your proportional term says spin the wheel this much, but the robot is not moving, it's not righting itself, and it's staying at that level. Well, the integral term will measure the sum of that error over time, and it makes the controller output bigger. So it makes it accelerates the correction. And the derivative does the opposite. So it's looking at the difference in the error terms, multiplying that by a constant. So this term kind of smooths out that jerky motion. So if you've got the robot really jerking back and forth, then by adjusting this constant here, you smooth it out. So that's kind of, a very high level view of a PID controller. And here's how I integrated the PID. And this is the original code I used, and you'll see the original code I used working. This is not the code I used. So I used code from this guy, Jupe Broking. And because what he did a non-linear, he figured out how to do a non-linear PID for calculating the step rate for the motor. So the core PID, you're just looking at, you're getting your pitch error, and you're looking at the pitch and the set point what the IMU is measuring, what you're supposed to want, and this is just a correction point that I had to add in. And here's the P term, the pitch error times the constant KP. Here's the integral term. I'm summing it over, all the errors. And then the D term is just I'm taking the derivative, the difference between the two terms. And here's my sum. And I calculate my PID, I feed it in here, and this then figures out the pulse frequency that I need to send to that 20 microsecond interrupt. So enough said about that. So here's the original code I had, and I call this the horror. So this is the kind of stuff that happened to the robot as I was trying to figure out how to get that PID controller working. So the robot would just go off on its own and would fall down. Notice the sticks I had to put in there to make sure the robot wouldn't kiss the pavement, kiss the floor. So this, it would start to work. Sometimes it'd work, then it would start moving. And notice the oscillation, how much it oscillates there. That's because of that P term. So this went on for hours and hours and hours, trying to tune the PID controller. So this is the code. This is running the code I developed. And sometimes this would happen. In this specific case, what had happened, I didn't realize it, was one of the PID connectors got unplugged from the motor. So the cable connecting to the motor became unplugged. That's why one motor is not moving. But it turned out to be great because it was able to balance really well with one motor. So enough of that. And then finally, this is my code. I was able to get it to balance, but what I couldn't get it to do was to drive forward. So this is my code. I finally managed to get the PID working. It was very jerky. It wasn't very smooth. And you can see it's oscillating a little bit there. Well, it's oscillating quite a bit. And if you push it, it self-balances itself. That's a real test. Are you guys seeing this okay?
Yeah.
Yeah, it's pretty cool.
And periodically it would drive forward and back, and that's just part of the PID controller I wrote. It wasn't very efficient. It worked. It would balance. So at this point, I could have just said, "Hey, it's working. I got it working," and I met all of my conditions. But I wanted to. You'll see later on. I wanted to get it to drive forward. So now here again, this is now this later in the video you'll hear my son laughing because he says that robot's having a seizure. Because as soon as I got it working, I took it up to my son's room. And I'm going, "Hey Tyler, look, it's working." Now see how it stops and it balances perfectly, no oscillation. That's because the grooves in the rug. It's got a little groove in the rug, and it's just making it stand still. So it just happened. It's not the code keeping it that still, it's the rug. So again, this is using my code. You could hear my son laughing there in the background.
Yeah.
And then, so what I did as a test, I was playing around with KiCad, and I wanted to learn how to send a board off. So I went and I got a board made for this, and I sent it away to JLPCB, and came back. It was about $6 to get 5 boards. I sent the Gerbers away, got it back, plugged in, soldered in all the parts, and it worked perfectly. Here's a test, the first test of the board. I didn't have to change a thing. It worked perfectly. The only thing I had to do was I had to recalibrate it so it knows what direction it was up in. So then the next step was I saw these sensors. These are ultrasonic sensors, and I had visions of the Mars rover, and I'm going, ooh, I wonder if I can make a rover. So the way these ultrasonic sensors work, there's a transmitter and a receiver. It sends out a sound pulse. It hits the walls, come back, and it measures the return time. So it measures the time it takes for the pulse to go out, the pulse to come back. It knows the speed of sound, and it can determine the distance from a wall. So here you generate a trigger signal for 10 microseconds. It sends out a bunch of pulses out. It measures it coming back, and then it raises a line called the echo line. And that line, it raises it the period, the time, the duty cycle of that pulse is proportional to the distance, twice the distance, because it's the return. It's the time to go there and the time to come back. So you have to take this and divide by 2 to get the distance going there. So I wrote some code to get it done. I use my 4 millisecond timer to say, okay, make a measurement. I use my 20 microsecond timer to toggle the pins. That pin that has to come up for 10 microseconds to say take a reading, and then I have a interrupt driven on the pin, on that echo pin, and I measure the pulses, the microseconds between the time the pin is high and the time the pin is low. And then I calculate. Here's the formula. Notice I have to divide by 2. The pulse width divide by 2, and I make some calculations. And in this, if the distance is less than 40, then I stop the robot. So, and I think this is the last video I've got. So basically the robot's going to drive forward. It checks the distance using the ultrasonic sensor. If the distance is less than, I think it was, is it 40 here? It's 40. So it's not, this should be saying 40. If it's less than 40 centimeters distance, stop. The robot stops, and then it turns approximately 90 degrees. That's where I have to measure the rotation. I have to use the gyroscope to measure the rotation to try and get it to turn 90 degrees. It pauses, it stops, pauses, and then it goes forward again, and it repeats. Now, this code is running the dupe broking PID code, and you'll clearly see how much more smooth the robot runs. I could not get this to work using my code, so I had to throw myself on a sword and say, look, you know what? I have to get help here. So if you look at this video, you'll see. So there it is driving forward, and you'll see how smooth it's driving. Now, the reason why it's speeding up and slowing down is because the speed control is like a PID controller. There it's turning 90 degrees, or it's trying to turn 90 degrees. It speeds up and slows down because the speed controller is kind of like a PID, but I only have a proportional term. So you'll see it speeding up and slowing down. If I wanted to do this right, I'll do a proper PID to control the speed. So I put my hand in front, it stops, and it turns 90 degrees. Then it pauses, and you'll see it oscillates just a tiny little bit. It's not much of an oscillation. So Jupe's PID controller works really well. See, and I stop it again, it turns 90 degrees, pauses. Then it rinses, it drives forward, sees my hand, it stops, turns 90 degrees, pauses. Now, look at the line in the floor here, and you'll see how well it's tracking. So you see it's not tracking very straight, right? The wheels are not spinning evenly, and it's probably not at 90 degrees to the wall, right? So, you know, it turns, I was really impressed there. That was almost 90-degree turn. So it hits this wall, stops, turns, and that's it. So that's the end of that.
Okay, that was pretty cool stuff there, Dave.
Very cool.
Yep. I think somewhere about 5 minutes ago, Hassan put his hand up. Hassan?
Was on top. The heaviest part of the robot was on the top of it. Wouldn't that make it harder to balance?
No, you actually want that. You want more momentum, right? Because it's like that pendulum. The further out it is, the more you can make it swing. You want more momentum you have. If it's light, you know, it's gonna swing too fast. So that like dampens out the motion, right?
Really? Because if you put the battery on the bottom, it would self-balance.
No, but you want it to be unstable. You want that weight to be up and top, because it's like a rocket. You want the fins to be above to below the center of gravity to make it swing, right? So if you've got the robot center of gravity higher, the wheels can change it faster. The further away it is, the less change you need, because the moment's smaller, right? The closer it is, the faster you have to make it move, right? It's that whole pendulum, first year physics thing. It's a pendulum, right?
Well,
Yeah.
Dave, I think you'd have to agree that if you placed the battery at the axle, near the axle of the wheels, that you would have less to correct.
Yes.
So it would be more likely to be self-stabilizing. I mean, your exercise was to explore the self-stabilizing, so yours made it more likely to fall over.
No, actually, I found the opposite. If I didn't have that battery at the top, because at first I didn't have it powered with that battery in the top, and had a power feeding it, the motor, the amount of turn the motor would have to make, it wasn't, I don't think it had enough turn. It didn't have enough resolution.
Okay, so the stepper motor so there wasn't enough resolution in the stepper motor to enact correction.
Yeah, because you have to have it up because
Yeah.
the stepper motor can only turn so much. And that's what I'm saying. It's a
Yeah.
pendulum thing. You want
Oh
it
no,
to
but
be
the
able
thing
to
is,
swing it.
limitation was the motor, which is an interesting
Yeah.
point. Because I think that point gets lost. I was thinking, these motors are capable of almost infinite resolution, and that's of course not the case at all.
No, and also too, you gotta keep in mind you're sending a pulse you have to send pulses, right?
Yeah, there's
And
timing issues.
I found these stepper motors, if you send it too fast to pull, have you guys ever flown RC models? Have you
Uh-huh.
guys ever used a brushless motor?
Uh-huh.
Okay.
No.
When you power on a brushless motor and you've got a brushless motor controller, the motor sings. That's the best thing I could say.
Yeah.
The controller makes the motor, sends out a series of tones, and it plays a musical tone. And
Yeah.
that's how you know it's armed. Okay.
Yeah.
And in the one video where I'm doing random, you can hear it singing because I'm sending it pulses so fast that it can't resolve it. So there's a limit. It's not an infinite. You can't send these things like pulses every microsecond or nanosecond, and it's going to respond to it. It just can't because these are coils. They've got inductance. They need time to charge.
There's real-time constraints on what you can control.
That's right. And so there's a limitation in terms of how fast you can get these motors. And I ran into that. That was one of the problems I had with my code, is because I was assuming I could control it linearly with the pulses, and you can't.
No.
Because if I wanted to turn the motor really fast, I had to pulse it really fast, and I was pulsing it too fast for the motor to react to it.
Mm-hmm.
Why don't you just stretch out your pulses and have a slower rate and more?
Because then the motor wouldn't spin fast enough and the robot wouldn't have enough torque to balance itself.
Are you sure you don't just need to tune your whole system a bit more? Maybe use a higher voltage, different pulses, because it doesn't seem right that
Hassan, there's a lot of variables you could play around with. This is just it was just me futzing around, playing around, just trying to get a PID to a controller to work. And in hindsight, it was a terrible PID controller because it's a non-linear system.
Should we discuss how you came up
this
with your constant?
What's that?
Should we discuss how you came up with your constant?
Yeah, trial and error.
Yeah, I was going to say, I had images of how long it would take. We have a person in our group here who has done this and expressed basically the same frustrations you did with the PID controller and with finding the proper constant, and the whole thing was almost, very parallel conversation. It's very tough.
Yep. Yeah, it is. And it was. I think you would have an easier time if you had a linear system, like a servo on an airplane. That you send the servo this pulse, and it's going to move 3 degrees, and it's a well-known linear constant. And so that's why airplanes and speed controllers for motors, they're all linear, and it's a lot easier to maintain. And I'm waiting for Kevin to chime in, because I know Kevin's got a lot of experience with PIDs.
Second order and first order.
Yeah, he's third in line. We had Peter up first.
Okay, actually, I probably got a whole slew of questions, but because there's a lot of questions here, I'll ask a couple of quick ones here, and then see what time we got left. Dave, mounting the sensor boards, does it matter the orientation of mounting them? Like you can mount them in the position you want, and then you calibrate it from that position?
No, you can't, because then you have to go through that whole trig math, and you have to figure out what the angle is. You have to go through. So if you change the angle of that orientation, just by taking that board and flipping it upside down, the way you measure the pitch is completely different.
No, I realize that. No, I mean, when you're designing it, do you have to design with the board saying this kind of a plane, or you design this kind of plane, or it doesn't matter?
Yeah, you have to. Yeah, you have to. You have to pick a plane. It doesn't matter what it is.
Yeah.
You could mount it this way, and as long as you know, okay, I'm going to be using my Y axis, and I'm going to be using my Z axis, and I'm going to be tilting those, then you could figure out the angles. But you have to know that that's a design constraint.
Sure.
You have to know which angles you can be using.
Okay, and one quick question here, just make sure I'm clear on this one. If your MPU there, when you're standing still, the measurement would be -1G.
Yeah, gravity. It would be if it's not moving.
Yes.
And it's flat. It's going to be measuring 1G coming down. But if you take this board and you move it up, that's a real acceleration, and that 1G now may go to 0, or it may go to plus 3Gs. Or if you take the board and you move it this way, all of a sudden there's a real acceleration in this direction, and so your accelerometer, this axis, is going to give you an acceleration value. That's what I was saying. An accelerometer is notorious for giving you errors based on real accelerations. So you can't use an accelerometer alone to measure pitch, because if that thing is moving, you get errors.
Okay.
Does that make sense?
Yeah, it does. Yeah. Thank you.
Mm-hmm.
I got more, but we'll hold on till later.
Yeah, we can have another round after this. Howard, go ahead.
Good, really interesting project, Dave. And since it's rate based, when it starts up, how does it know where it is if it hasn't moved?
Good question. That's why you have to use the accelerometer. You always seed an accelerometer value. You start off with an accelerometer value, you seed that, and you hope it's right, because if it's accelerating, you're going to get a wrong answer. You're going to get a bad initial condition. So you take your acceleration value, your pitch, right? And you see that's your seed. Then you work out, you correct that based on the acceleration, on the gyro rotation. So you don't use the gyro value as your initial value. You use that as a correction to your accelerometer value.
Oh, that makes sense. So yeah, that's very interesting, because I've used both race-based autopilots and AHRS-based autopilots, and the difference, yeah, I know what you're saying between linear and nonlinear. It's amazing. So, but really interesting project.
But I think in those systems, they're actually using real gyros. Like if you look at the older airplane IMUs, you know, even that not the what's the artificial horizon? That's got a whole bunch of gyros inside spinning, and that's why when you're airplane, do you fly?
Oh yeah,
Do you fly,
yeah,
Howard?
but the
Okay.
modern the modern system,
And that's why
the modern
yeah,
system
it's all
have AHRS,
electronic now.
like
Yeah.
it has
Yeah,
sorry, go ahead.
Yeah, I was going to say back. Remember the Cessna 150s, and you know the what are the the low wing Pipers? You know those things. You had to go do a run up and get the gyros to spin up in order for everything to get balanced. And once everything's balanced, you can go flying. But yeah, nowadays everything's electronic, right? So I don't think I don't know. Do airlines still have spinning gyros?
No, it's called the short form is AHRS. It's called Attitude and Heading Reference System, and essentially, it's like you say, it's a linear that measures pitch and roll. It's not a rate-based system. The old autopilots were rate-based systems that had actually mechanical gyros.
Yeah,
and like you
but
say,
they would have to get some kind of data to correct. If it's the non-rate system, they have to have, because every sensor has got some errors, so you need to fuse multiple sensors together to get an accurate value, right? So I don't know how it works, but I would imagine they would have some other types of sensors, and they're fusing the data together using a Kalman or complementary or some other filter.
Yeah. No, thanks. That's interesting.
And Kevin, go ahead.
Yeah, it was interesting, Dave. Thanks. That was good. But did you look up Ziegler-Nichols? It's an
No.
empirical method for tuning a PID.
Oh, no, I didn't. This was all on my basement floor, Kevin.
No, I mean, it's sort of an algorithm for tuning a PID and more in process stuff, but just because it looked like you had too much integral. When it's running off like that, usually that's a symptom that you've got too much integral in there, and it's just integrating away and off you go. When you were first on your first video there, but
I did have a pretty big integral term. I didn't have a big integral term. I think I had I'd have to go back. I think I had a large derivative term and I had a large proportional term, but I don't think I had a big integral term because I found you use too big an integral term, it would just go whoop, it would just fall right over because it was integrating too fast.
And that's I mean, that is the trick, right, with the PID stuff.
Yeah.
But couldn't you linearize it by like taking your error and dividing it, or doing a trig function on it, like sine or cosine? Because you don't need much gain when you're vertical, right? You need a lot more gain when you're way down.
Right, and that's where the trick is, right? Is if you look at it, that's why my PID controller worked, because I use more of a linear approximation, and that's why I was able to balance. But you'd got a lot of oscillation, and it would drift a little bit, but it always come back, and it was always oscillating, right? It wouldn't converge on a straight point, right? And so yeah, you're right, and that's why my thing worked. But if I wanted it to have a constant lean to be driving forward, that's when I couldn't manage that. My PID controller wouldn't work. And so that Juke Broken guy, he does a logarithmic. He does, you know how log is an expansion? He does an expansion and he takes only the first two terms and he kind of gets it to become linear. But yeah, and I think it was a tough thing for me to tackle for my first PID controller. I think I should have tackled something a little bit more simpler, easier.
Yeah, I mean, if I was going to do that, I would probably use some feed forward in there too. Like if I wanted to drive it, I would do some feed forward and let the PID just control the angle you want, and then you set the speed for the motors around that.
Exactly right, and that's where I had that set point. So I would say to drive forward, I want my set point to be plus 10 degrees. So it would correct, and it would measure 10 degrees and hold 10 degrees. So if it goes more than 10 degrees, it would come back, and if it goes less than 10 degrees, it would go forward.
No,
so you're 100% right.
But by feed forward, I mean go around and say, if I want to run the thing at like 1 meter per second, the motors have to go this speed, and then you set your 10 degrees on top of that, so that you let the PID control, and then the PID doesn't need much gain. It keeps the PID gain a lot lower and makes it more stable.
So
we do that in industrial stuff all the time. You figure out where you need to be, and then you let the PID just have it like 5 or 10% trim.
So it's kind of like a bias, a DC
yeah, exactly. Bias. Yeah, the PID doesn't have full control. I rarely do that now.
Okay, I never even thought about doing that, but that's probably a good way of doing it, right? Put an offset in there.
It lets you have a lot lower gain on the PID, so therefore it's more stable generally. Yeah. Anyway, that's my 2 cents.
We should have one weekend at Dave's floor, as Peter pointed out. Peter, you can go next, but can you take the floor? I got to take a phone call here. It's important.
Okay. Yeah, no problem. Dave, you mentioned you use Visual Studio and Platform IO. What's the difference between the two? Yeah. Or are they complementary?
No, Platform IO must run in Visual Studio, or it's called Visual Code, or I think it's called Visual Code. It's not the full. There's Visual Studio, which is the big Microsoft development platform, which you got to pay for to go and use. And then there's, I think it's Visual Studio Code, which is a free version. But you need a platform IO must run in Visual Studio Code. You can't just, it's not a, it's like a plugin.
Okay.
Can I explain that to you? Visual Studio is the professional compiler. Visual Studio Code is just an editor, but and it's free and open source. But it supports a huge marketplace of plugins.
Yes,
And Platform IO is just one of the plugins. It's basically
that's
just
right.
a make and build system, and you can install the free Arduino compilers in there. And so that's just taken off like a rocket. So nobody uses Visual Studio anymore. They all use Visual Studio Code.
Okay. Eric.
Is it the Platform IO or the Platform IO IDE?
No, there's no Platform IO IDE. Platform IO, as Hassan said, Platform IO is a plugin that does the compilation and linking to generate the Atmel code that's going to be burned onto the chip, that's going to be sent to the chip.
Okay. All right. So it's just straight Platform IO.
Yeah, yeah.
All right. Thanks.
Dave, your I think it's A4988 board. What's the maximum current you can pull out of that board?
I can't remember, but I know it's amps.
Okay.
It actually comes with a heat sink. If you look at the board,
you're going to use the heat sink on Phoenix?
Where is it? Stepper. See, here's the module. There's the module there, and you could see you could see the chip there.
Yeah.
And it comes with a heat sink that you stick on the chip. And that chip gets hot. Like with this heat sink on that chip, you put your finger on it, you will burn your finger. It gets hot. But that's when I'm really exercising it. Like I've got the wheels spinning and I'm like, they're really spinning, right? But when I'm pulsing it back and forth, it doesn't even get warm. But if I got the wheels spinning really fast, like that test I was doing where it's going and spinning randomly, that chip gets hot.
Okay, thank you. Hassan.
Yeah, what was the pulse width on your stepper motor drive signal?
What do you mean the pulse width?
So how you were stepping you were pulsing your stepper motor drive waveform. How quickly were you pulsing it?
Well, it depends on what the PID output was.
So
you pulse it based on your PID output, right? Your PID output is going to tell you how much to pulse it to make it come back to straight.
Was it like a megahertz or something? Like what, every microsecond?
I like, as I said, I had a 20 microsecond timer that was going off at 20 microseconds. So the fastest the pulse could be was 20 microseconds. That's the period, fastest. And then I would count that I could delay it up to a millisecond if I wanted.
Okay, I think that might be one of the issues because, I mean, like a stepper motor ought to be more linear than a servo or anything, because servos and stuff, you apply a voltage or whatever, and you know the motor tries to spin as much as it can, and the actual amount it moves depends on the load and stuff. But with steppers, you apply a fixed number of pulses, and you know exactly how much it's moving. And so maybe you're just pulsing it too fast, and it's burning power in the drivers. And if you use this, like, I don't know, 1,000 steps per second, that might have been good enough. You would have got the same result, but you know, a lot less power, and probably would have been better overall. I think the problem is that we're pulsing too fast, maybe.
And also keep in mind, Hassan, that the shorter like your PID, okay, you're measuring error and you're multiplying it and you're getting a output. That output, the bigger the output, okay, the bigger the error. So the more you have to move. So you've got a bigger number, PID number, which equates to a smaller pulse width, because the faster the pulse width is, the faster the motor turns. So if you got a big error in terms of how far the robot's leaning, you have to take that PID output now, and you have to convert that into a smaller, narrower pulse width. It's a non-linear system. And I think Kevin put his hand up. I think Kevin could probably explain this a lot better than I could. Ken.
Yeah, no, I wasn't. Yeah, just Hassan, just for this, the speed and torque on the stepper and the servo. Steppers normally, you can get a lot of torque at low speeds, but it's a nonlinear torque curve too. The higher you go, the less torque you can get out of it. Whereas a servo, you'll get constant torque over the entire speed range. And a servo can regulate position just as well as a stepper because it's got an internal torque loop, right? So if it doesn't get where it needs to go, it applies all the torque it needs to get there. And you're right, it's discrete steps on a servo, or sorry, on a stepper. But a servo can do pretty amazing position regulation as well. And there's a lot of reasons that you don't use steppers, especially in high inertia loads and stuff, because they don't like inertia. That's the other thing. Whereas servos can deal with it because they've got a torque loop, an internal torque loop. So, but anyway, yeah, it's getting into the the nuances of control theory.
Oh, I see. So if you apply, okay, so if you want to move us, I guess with a stepper motor, you have to go smaller micro steps to kind of, and a lot more of them if you want to get high torque. Whereas if you just kind of
yeah, you have to do it slower. You can't do it at high. You can't get the same torque at high speed that you do at low speed, and that's all with, like Dave said, with the inductance of the coils and stuff. You just can't. You can't put in that much current, right, to change the magnetic field that fast. Whereas in a servo, if I ask it to go 0 to like, I don't know, 1,000 RPM in half a second or something, it'll put like 300% torque in there right up to the point where it gets up to the speed set point, right? And then it'll back right off.
Did you have to do voltage control to
Yeah, servos have a linear voltage characteristic on the motor, right? So many volts per 1,000 RPM on the coil, but then they have a torque loop inside that determines how much current's actually going to go or what the frequency does. It's like that. Then you get into the IQ motor model, right? Anyway, the math is way beyond me, and it's also very nonlinear too, from what I understand.
And the toy grade servos, the hobby grade servos, they're based on a PWM. So you set it, I think it's between 1 to 2 milliseconds, your pulses. And so 1.5 milliseconds, it's right at 0. And if you go 1.4 milliseconds, it turns like a degree or 2 degrees. If you go 1.6 milliseconds, it'll go the other way, one degree. And it's very precise. And Kevin, I think you're right. It'll apply as much force as it needs to get to that point. And once it gets to that point, it stops.
Yeah, I'm talking about servo motors. You're talking about servo positioners. So they're two different things. But I'm talking like a regular rotating servo motor that just spins at some speed. The best demo I ever saw on that was some guys from Yaskawa came in, and this was years ago. And they took, I don't know if you can see this, but this is a 0.5 millimeter pencil lead. And they had 3 of these connecting 2 discs. So they had 2 discs with 3 pencil leads like this in between them. And each one was driving a separate motor. And this thing would spin up to like 2,000 RPM and back down just like that fast and not break the leads. And they were position regulating the servos between them. It was a pretty impressive demo because these things are very, very brittle, right? So anyway, that was, that's over 20 years ago. I can't imagine what they can do now with some of the servo stuff.
On that note, Kevin, so a servo motor always has a controller built in. Is that correct?
Well, or yeah, you need a controller for it. Yes, a servo motor. Yes.
All right, so that simplifies everything else because now you only have to tell it the angle to move to, and or speed. I guess a servo positioner, you give it the angle, and a servo motor, you give it the speed.
Well, it depends how many loops you have, right? I mean, so if you're regulating position, you're going to have a position loop that drives a velocity loop, and the velocity loop drives the torque loop, and the torque loop determines what the motor really does.
Ah, interesting.
So if you don't want to control position, then you get rid of the position loop. You just tell it how fast you want to go. And if you don't care how fast you go, then you just say how much torque you want.
Interesting. And I read in a book somewhere that, I mean, hobbyist servo motors, less than $200, are just complete junk. And that if you really want to use a servo, you should get the good ones, the industrial ones. Do you know if that's correct or?
I don't know anything about hobby servo motors much. I mean, they're probably okay for hobbies, but yeah, if you're going to do industrial stuff, yeah. I mean, I just ordered a bunch today, and yeah, they're several $1,000s for even just a little couple of horsepower motor, right?
Couple of horsepower.
Yeah.
That's pretty big.
What, the horsepower or the dollar sign? I was
going to say, yeah.
That's taking inflation too, eh? Okay, go ahead, Pete.
Just to change the subject slightly, Dave. Right at the very, very beginning of your presentation, you talked about the autopilot that you were building and played around with for a while, way back when. So now that you've kind of dusted it off a little bit, if in memory anyway, are you going to go back to that project and see if you can beat it?
What's the point? You can go and get these controllers now, like nothing. So there's no point in going there. It's like going and saying, I'm going to go build my own transistor, right?
Well, but you know what? The curiosity factor might say one day I'm going to do that. If Jerry Ellsworth can do it, why can't I?
Why brew your own beer?
What I think I might do is I'm going to go use I'm going to go use the controllers you can get, and what I'm going to do is I'm going to make different interesting types of aircraft. So make like a aircraft that the wings it's like a vertical takeoff. So it's going to take off this way, then it's going to go forward and start flying. So stuff like that I might do because then you're using controllers that are off the shelf, and you just have to go and program in. They're all PIDs, by the way. All these controllers, they all have PIDs. So you got to go in and tune the PID to get it to like use dual motors to make it level itself.
Okay, any more
Dave,
questions?
you had a question. So Dave, you had a single PID, so you were kind of controlling position, but velocity and torque were just sort of assumed to be fixed kind of thing.
Yeah, I didn't, as I said, I was doing, if you look at the speed I was doing, I was just setting the speed to a value, saying, okay, I want 10 degrees of pitch. And so it would pitch 10 degrees. And in order for it to maintain that 10 degrees pitch, it had to be moving. So, and that, as it's moving, you'd see it, it'd slow down, it'd speed up, slow, speed up. And that in itself was kind of like a PID controller, but I was only using a proportional term. So if I was to go in and use, a integral and derivative term, I may get it to run smoothly. But what Kevin said makes a whole lot of sense. So what you do, you apply a bias to the motors to say, I want the motors to spin at 3 RPM. I'm just making up a number, or 60 RPM. I want the motors to spin at 60 RPM, and that's my DC bias, then I want it to balance.
Right. So essentially your torque and velocity were unregulated, basically.
Yeah.
Interesting. And how do you measure angle again?
Using the accelerometer and the gyro.
So you know the gyro tells you, okay, the gyro tells you the angle from vertical.
The rate, it tells you a rate. So you have to multiply that by how fast you're sampling it.
So you're integrating
the gyro. How fast you're sampling it. And so basically you're integrating the gyro over time, right?
Right. Interesting. That's really cool. It's actually neat. Yeah, thanks.
Did you have another comment, Peter? Oh, I'm sorry. I thought I saw your hand go up.
I thought I had enough comments, questions for one presentation.
Well, has anybody else got any comments or questions? No. Okay, Dave, that was great. Some of it was over my head, but it was great. That was pretty cool stuff. Now, I think, Pete, you got one more thing to do, 5 minutes worth?
If that.
Yeah, okay.
It's just sort of like maybe a little bit of a show and tell or something like that. I don't know. It was just I decided to do a little bit of a rainy day project the other day, and it was basically a test amplifier that on the Phoenix receive board I was messing around with. I wanted to output it into an amplifier. Anyway, I thought I think it was last Sunday, or anyway, the weather wasn't great, and I wasn't going to do any outside work, and I thought, let's have a go at the board. Nice, easy board to do. It's nice to get at it. So, what could go wrong? Well, it turns out a few things can go wrong, and one of them I blame on Dave, but we'll get to that in a minute. And the one thing is, there was a couple of lessons I had to relearn on this project. Many years ago, I learned the hard way that tantalum caps have the positive end that's marked with a black band and not the negative. But apparently I had to relearn that lesson on last week as well, because I soldered in backwards and let the smoke out of that cap. And then when I took that cap off, I lifted a trace. So then I had to patch up the trace. So the next thing that happened was I could not get any power out, scoped it out, and determined that, okay, I guess maybe when the cap shorted or overheated, I somehow took out the transistor, because it has one transistor, 3904, and also an LM386 chip. So I took the transistor out, put another one in, still wouldn't work. I thought, okay, what's wrong with this? Scoped it out. And yeah, it's still the same thing, signal not getting through. So I thought, well, what are the odds of a second one going? So I looked into a little bit further, and this is where I'm blaming Dave now, because Dave asked me to proofread a circuit of his, and he forgot one trace. And all of a sudden now I forgot a second trace. So what turned out to be, I thought was going to be a nice looking little board, is kind of turned into a little bit of an ugly board. But anyway, there it is there. It's pretty hard to see the repairs. There's a repair up there, one trace. And then underneath that cap is where there was the missing trace. Down there is the transistor, the 3904, and of course the LM386. So, and then I mounted the pins in the pot volume control on that side. Anyway, it works really well, quite loud. When I plugged it in and turned it on, it just about deafened me there. It has that much audio power in there. I was quite surprised. So anyway, so what I learned, again, another lesson I learned there is there's no such thing as a pleasant Sunday afternoon project. That's it for me.
Oh, that's that little story you put up on the on our group site.
Oh yeah, that's right. That's right. Oh, yeah.
Yeah, and I commented, it sounds familiar. Usually something like that, I'll leave it for a day or two and then come back to it.
No, but you see, this was like the idea was to build it, and then I could use it later in the day or that evening to carry on with the Phoenix project. But by the time I finished with all anyway.
We've never been there before, right?
Yeah. No. Peter's the only one that smokes parts. Very good, Pete. Cool.
Yeah, he doesn't. At least he doesn't smoke his test equipment.
I've heard he smokes other things too.
Well, I talking about smoking test. Well, yeah. At least, you had to send yours back, but it was still under warranty. I'm not sure many guys. My spectrum analyzer reads about 3. I think it's a 3 dB or 4 dB low, but it's consistent across the whole range. So it's not a huge deal, but it's still something that bugs me. Anyway, it has been for a while. So I ended up recently getting in touch with Siglet, our friend Jason, and basically said, I'm not a professional. It's not used in the professional capacity. Can you guys tell me how to open up the back so that I can make a tweak to a little pot there just to bring it back up so it at least reads there? So I didn't hear anything for quite a while, reminded him about it, and then he said, okay, I'll send it off to the technician or one of the guys in the lab. Anyway, didn't hear back from him. I wanted to touch base with Jason on another topic. And while I was talking to him about that, I brought this up, and he said, "Oh, I'll look into it." Anyway, he kind of came back and he said, "Ship it to us, and we'll charge you $900 and some odd dollars US." And I thought, because you're out of warranty, I thought, oh god, so $900 and some odd dollars, $950 US, plus the shipping. I don't know what the shipping would be there and back, because I'm sure I'd be responsible for that. So that's probably going to push it up to about $1,200, $1,100 US. Which is just about what I paid for it a few years ago, because I think it was what the show special was around $1,300 US or something like that. Anyway, so I'm going to live with a consistent 3 dB. Now I did have a horror story as well, because all of a sudden it started to read 80 dB low, and I thought, now maybe I did fry it. I've done a Dave, but it turned out I had a bad cable.
Yeah, go ahead, Kevin.
Yeah, I was just going to say, Peter, that sounds about right, because most industrial stuff now, to repair it, is half the cost of a new one. That's the standard quote. If something's broken, it's take the new price, divide by 2. Doesn't matter what's wrong with it.
But it doesn't. But it's not even broke. That's why
I know, but it's like if they have to touch it, it's like they want to charge you for it. It's silly,
I mean, I thought Dave had earned enough brownie points from Sigma a few years ago that they would have told me what pot to adjust.
Or he pissed them off enough they didn't want to.
Hey Peter, you know that Dave Jones has done a ton of teardowns of SAs and scopes.
Mm-hmm.
He might be a guy that you may want to just fire something off to, because he might be able. Chances are he's not going to tell you, go turn pot 305, 1.5 turns, and you'll be okay. But at least he might give you some guidance to say, oh, you know what? In order for you to do that, you got to blah, 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 blah. But there's also, I seem to remember, wasn't there a guy in Hamilton that used to repair oscilloscopes and test equipment?
I bought a scope off this guy. He had a small warehouse close to the steel mill.
Yeah, doesn't that guy doesn't he repair stuff, Hassan?
Yeah, he did. Yeah, he does repair stuff. I think I talked to him once about something, but I think I saw him at one of the ham fests in Brampton too.
So that might be something, Peter, you could look at. He might be a fraction of the price, or maybe he might just tell you, oh, it's pot 306. Go turn that.
I mean, I have a funny feeling it's a little bit more than just turning a pot, but you know what? You never know until you ask, right?
I think it's software. I think there's going to be something. It's going to be some constant in software. You got to go and change.
Oh no, it wasn't like that originally, Dave. It wasn't like that originally.
There's got to be somebody local who can look after this.
between my signal and SIGGEN and my SA, it's off by about 1 to 2 dB. If I connect my Signalant SIGGEN to it, and I just do a pure sine wave, I set it, say, at 10, minus 10 dBm. I measure it on my SA. It's off consistently by about a dB or so. But you know what? Your cables, your connectors, all that stuff, adds a quarter dB, an eighth of a dB, or a dB here and there. And so it's very easy to chew up a dB.
To be honest with you, quite frankly, since we got back into the Phoenix project, I'm now becoming far more comfortable with the absolute measurement. With relative measurements with the spectrum analyzer anyways. So it's not a huge deal for me today as it was several months ago or a year ago or whatever. Anyway.
Okay, I think, Michael, you had your hand up.
Dave, since you're talking about scopes and the like, the 1202X, the one I have, the 200 megahertz scope, it has, it's got a 1 meg input, but apparently it looks like the manual talks about having 50 or 1 meg, and the scopes just don't do that.
No.
Do you think is that a firmware thing? Do you think, like the firmware can't hear you? Sorry, I can't hear you.
I'm on mute. Michael, that's an interesting point. When I first got my scope, okay, and I turned it on, and I went into, there's somewhere you set the load or something like that. There was an option to set the load to 50 ohms. And I thought, holy shit, this scope can do 50 ohms. And I went back to Jason and I said, Jason, I didn't realize this scope can do 50 ohms. He goes, that's a firmware bug. Upgrade your firmware. Sure enough, I upgraded the firmware, and that option came off of the menu.
It disappeared.
It disappeared. So you may have old firmware local.
But it didn't work anyways, though, did it, Dave? It didn't actually work. 50.
It didn't do anything. Because if I go to high Z or 50 ohms, I'd make the same exact measurement. There was no difference. And so I was asking him about that. That's what it was. I asked him, how come it doesn't show a difference? And he said, oh, because it's a bug. He said it's the wrong firmware. That firmware loaded in your scope is for another scope.
So when you upgraded it, that disappeared.
It disappeared.
The POM option disappeared.
In the FFT function, it'll do dBm for you, but you have to set the load of what it's measuring. So if you're measuring a 50 ohm circuit and you're probing it with your probe, you set it to 50 ohms, it'll calculate it as if it's measuring a 50 ohm load. So it'll actually give you dBm based on 1 milliwatt into a 50 ohm load.
Mm-hmm.
So the scope does do that, but you have to set the load. So you could set the load to like 100 ohms or 1K ohms. And it takes that, it calculates the power into that load, and then it calculates the dBm.
Yeah.
Do you understand what I'm saying?
So yeah, I think so.
Yeah, it works backwards because if it knows the load, then it knows the voltage. It could figure out the power into that load, V squared over R, right?
Yeah. Okay, thanks. By the way, that was a really impressive presentation.
Yeah,
I thought.
Yeah,
I'm curious to know the graphics are just beautiful. It's completely off topic. Did you do those graphics yourself? All the diagrams and stuff in the PowerPoint?
No, most of the stuff I get, I steal from the internet.
Okay. Yeah.
Google.
Yep.
Open source.
Yeah. Probably half of this the stuff is copywritten.
Yeah.
Good artists create, great artists steal.
If you go to jail, Dave, can I have your robot?
Sure. You're gonna lose a lot of hair with that thing. Look at my hair. See it thinning out? I spent months and months and months trying to get that stupid thing to work.
That's from lying on the floor with your forehead.
Yeah. But you know, and that's why I always preface my talks with, you gotta push your limits. You gotta try and do something, which it's not easy. You do difficult things. Isn't that what JFK's speech about the moon? We don't do these things because they're easy.
How does that compare to the NXT PID stuff we used to do?
Oh, it's NXT stuff. That's all in LabVIEW, right? That was dirt simple.
Mm-hmm.
Okay.
But I have visions, Eric, of this thing running across the floor, and I'm going, I wonder if I can make this thing do a line follow.
Sure, you should.
Hey, was
Where's
anybody
the
in your
camera?
house? Was anybody in your house impressed with what you did, Dave? The family impressed with what you did? The wife?
Tyler.
No, my wife goes, you need a life.
Or you're such, or you're
playing
such,
with that stupid thing on the floor.
or you're such a nerd.
Hey, you're here for it.
But she says that only when Eric's around. She goes, "You guys are such nerds."
Until you have her
and
bring,
me.
have it bring her a tropical drink that's balanced on a platform.
Yeah, she'll be impressed then.
Yep, got to do.
Yeah, that's the first thing she said to me when we met. Such nerds.
The wives are not impressed with what we do. It's funny to mention that because my wife sent a picture off to her brother and sister and said, "Here's Peter's bedside reading." And it's in the latest QEX magazine. I forget the exact title because it's about 2 sentences long, but it's like impedance measurements, methodologies made easy, blah, 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 complex math, whatever they had. Anyway, this big long title. And then she says, and here's mine, Murder Mysteries 101 or something like that, from her like that. So they're not impressed.
Last time I was up at the cottage, I brought the Art of Electronics, and that was sitting on the, the cottage reading table. Sandy said, "What the hell? Look what he reads." Sorry.
Well, I went down to Florida. When I was in Florida last February, I brought down EMFRD.
It's a fine text.
Eric, look at your phone.
Look at my phone. Nice. Yep, that's pretty much it. You should share that with everybody.
I don't know if I can. I don't know if. Let me see if I can pull it up.
That's how it works.
This is how we. Oh yeah, here. I think I can get it. This is Peter. This is what happens when we.
At
okay,
the beginning.
here it is. Here. Here's what.
At the start.
Man.
Not sharing yet.
I know. I got to get the image. It's just not coming up full screen.
Everybody's okay with pornography, right?
As long as it doesn't involve Dave.
Yes, please.
Or anybody that I can see right this moment.
So Peter, this is kind of like this picture here reminds me of us doing one day at Eric's. Here, let me share my screen.
I don't know. Don't know how this works.
Here, I could do it. Here. Okay, can you guys see my screen?
Yeah.
Okay, so Peter, this is what I said to her.
Oh yeah. Yeah, you're right. That was one. Well, it's whenever we get over to Eric's, no matter where it is, his house, his farm, his cottage, it doesn't matter.
Yeah, so that picture reminds me of us going over to Eric's. You know, we always go, oh, radio. You know, we're talking radio, right? And then we say, okay, let's have a drink. Next thing you know, we're around a fire and we're stumbling around.
Well, look at our second annual Rat Hole convention, where we emptied all our rooms out of any booze that was left over. We all met by the pool and sat around the picnic table and polished it all off.
Yep.
Yeah.
Is that the sun coming up?
Yeah.
Okay, guys. Anybody else have anything?
No.
Okay. So, bid you all a good night, and we next meet on the December 7th. First Wednesday.
Yeah, that's me.
And I'm going to do a presentation. Peter, when am I supposed to do that presentation on sideband inversion?
I'll take a look. I think Michael, you're on the 21st, right?
That's right. And the presentation's coming. I'm gonna have to rebuild my oscillator circuit, but aside from that, it looks okay.
Okay, so you're December 21st. So how long do you need for yours, Dave?
Oh, it's standard Dave 20-hour.
No reason why we can't do it. Well, we could do it during the mixer, can't we?
Yeah, I don't know. I still have to, as I said, I still have to go through it. I went through it once, and I'm going, was I drinking when I did this?
We should set aside a 2-day weekend for his.
Either that or into January, or
I was going through it, and it made no sense to me.
Ken, would you be ready for December? Kevin?
Yeah, more than likely.
Okay, so we can push yours into the January regular meeting, Dave.
Yeah, because that presentation, after our conversation about the crystal filter and what side of the sideband do you put the BFO, low side or high side, that has to do with sideband inversion, which side you put it on, right?
Yeah.
And so that's really, back when I did the D612, that was something I had to learn the hard way, is that depending on which your front end mixer is it minus or plus, and then your BFO is going to be the opposite side.
Yeah,
depending if it's minus, it's got to be the opposite way. It's got to, because if you do a minus, LSB becomes USB. So then you mix it as if it's a USB signal, your BFO. Then you get sound coming out.
All right, so let's do that in the January regular meeting then. That gives you time to get your head straight.
Yeah.
Okay.
Okay, so I guess we're done now. Okay, have a good evening, everybody.
Okay.
And we'll catch you in a few weeks.
Yep. Good night.
Okay.
See you later.
Okay, good night, guys.
Thanks. Good night.
Oh, Dave, you know what I just read the other day? Where'd he go? Oh, he's gone. Oh, well.
Yeah, it's fast.